Hello all, in this video I will show you how to implement efficiently a merge sort algorithm, and I will contrast it against the so-called trivial implementation, which keeps allocating memory for doing the merges. So first of all, I need a method which will create a random integer array size, and what I do is return new random import int. Okay, to array, of course. So next step is to validate that the input integer range is sorted. So what I do is so I will implement the general implementation, which can concentrate on only one particular sub-range of an array. So what I do is finally return true, but int I from index to, I need to leave one element first so that I will not end up in a array out of in the array index out of range, because I will operate in pairs of indices. You will see it shortly. So the if array is somehow integer at position I is larger than an integer at the position I plus 1, we have an inversion, and we know that the array is not sorted. Turn false. Okay. So I will overload. Okay, I will specify another is sorted, which checks for entire array, and it does only this array starting from index 0 to go through entire array. Okay, sorry, length, yes. Okay, next one. And I will start from so-called trivial merge sort. Public void trivial merge sort asks for an array Okay, I have a line which is longer than 80 characters. I don't like that at all, so I have habit of putting all the arguments in a stack. So okay, by the way, I use the same semantics as sorting methods of Java library, Java development kit, and the point is that we have an array. From index is the smallest index pointing to a range which we want to sort, and to index is largest exclusive. Okay, smallest exclusive. Okay. The point is that I will sort actually array from index to array index -1. So I will sort this range. And the good point about it is that I can easily compute the length of the input range needed to be sorted. So the base case, if range length is 0 or 1, it is trivially sorted, so we return just. Otherwise we do the following. Okay, we allocate two arrays, left array is new int around half of the range, then have this okay, range length minus left. So I have um, two empty arrays, and next I will keep populating them with the contents of the array. Yeah, I need another index to the input array. Starts from index, and okay. Next I will populate the right array. Int e once again from 0 to right array, and keep incrementing the index into the input array. J from index plus left array length. Okay, and okay, I have these two arrays populated, so what I do is sort them recursively. Sort left array from index 0 to by the way, actually I could do this. Well, let's trivial mergesort the entire array. Yeah, so this one will sort entire array, whatever array is. So actually I don't need this, which is nice. Now the last step is to actually merge the two arrays. So int left is 0, okay, and int target index is full index. So while left okay. And finally we add the leftovers to the sorted range. Left array so what comes to these two last while loops, only one of them will iterate at least one time. So for another part, it's just a no operation. Just one check and we are done. Okay, so well, I think we're ready to actually try our trivial merge sort. So we get an array 1 actually, get an array of size 20, let be. So okay, let's see, fingers crossed. I can treat this, so I think I will just call sort is sorted. Yes, it is sorted. I need another array actually. Yeah, I can just clone it. So let's now write a more efficient merge sort, and we start by efficient merge sort entire array the same basic check. Sorry, smaller than 2. Trivially so. Um, hmm. Now, so this means divide by 2 actually, and discard the decimals. Okay, so the actual implementation routine is like this one. So we have a source array, we have target arrays, and we have in offset in source, offset in target, and the actual length of the range. Okay. So what we do is we need a auxiliary memory buffer, and actually everything we do is just So as you see, the first argument is the source array from which we take elements, and the second one is the target uh, array in which we put our results. So basically, we start on the top of the recursion level, and we copy the range, and we keep inserting new elements from the buffer to the actual array. Just like this. So 0 array for index aux half range length, yes, array from index plus half range length, yes, okay. And the next step is just to sorry guys, actually no. This is everything we actually need. Sorry. Oh man. All right. So we need a condition to stop recursion. So we first sort okay. Okay. Sort the left chunk. And finally we do the merge. That is what offset. And finally we dump the leftovers. Source left target get index left bound minus left slash right target index and right bound is right. Just a moment, I have to functify this code a little bit. So, okay. Next we will actually profile the two algorithms or measure how much time they take on the same input. So what I want to do is use a larger array, first of all, like 1 million. 1 million. And then we'll profile the efficient one. I need to sort its own array, so array 1, array 2. So and I have to check the array 2 as well for being sorted. And finally just will assert that they are equal. Okay, let's see what we have. Oops. And the last point I will show you in this video is that if you work with Java and you want to profile your algorithms or measure how much time they take, you need to warm up your virtual machine. By warming up, I mean that you have to run some dummy data on your algorithm so that Java virtual machine can optimize your machine code and make your different algorithms comparable. So what I do is warm up. So I will make like 50 warm up iterations, and in each one I will sort some data. I'm not going to compare them, just okay, we are ready to go. Oops, I was not. So it's warming up now. Take some time. Okay, as you see, The efficient one is actually a little bit more efficient than this trivial merge sort, and the problem is that you um, keep allocating memory one over and over again. Actually, the space complexity, or not space complexity, but rather in the efficient merge sort, you allocate just the auxiliary array and reuse it. In this trivial one, you keep allocating memory over and over again, and that's what it slows down a bit. So let's compare once again. I think it should be more difference on large arrays, I think. Okay, almost 8 seconds, and the efficient mesh sort improved by 2 seconds, so here's the difference. But anyway, thank you for watching, and if you have questions or propositions or something, just leave me a message or leave a comment on this video. Thank you guys, see ya.